So determine if the mean value theorem and or Rolle's theorem can be applied. And if so, apply the appropriate theorem. If not, explain why. All right. So, well, let's see. Well, one of the conditions involving Rolle's theorem was that they had the same y values for given value of x. Right? And those given values would be the endpoints. Right? But for the mean value theorem, it wasn't really anything more than continuous and differentiable on the closed interval. So, I mean, if you go back to the theorems themselves, if it's continuous and differentiable, then all we're looking for in the mean value theorem is that there would be some location on the interval where the instantaneous rate and the derivative are the same. Right? But Rolle's theorem is the one that had that added component. Oh, I don't even know what's going on here. That's strange. That added component of f of a being equal to f of b. And these are some stray marks that really shouldn't have been there. Right? So if I can evaluate the first f of a equals f of b to make a determination of whether Rolle's theorem would apply beyond whether or not there is a continuous slash differentiable function on the closed interval. Right? So starting with number 5, this one is continuous and differentiable. Let me get a thicker pen here. On the interval of 0 to 2, right? And the reason we know that is because it's a polynomial function, right? Polynomial functions are continuous and differentiable throughout their domain. And the domain is generally negative infinity to infinity, right? So just by knowing the nature of the function, we're able to state continuity and differentiability. Right? I mentioned this last time, where if this were the first unit, then we might have to show it using limits, but now we can just sort of take it for granted based on prior knowledge, right? So that tells us that the mean value theorem would apply. I'll write that out in a second, but what I want to do is determine f of b and determine f of a and see if they're equal to one another, right? So f of b is equal to, well, f of 2. F of a is f of 0. I'm going to see if those are equivalent to one another. So if I plug in a 2, I get a 16 minus 16, which is 0. If I plug in a 0, I get a 0. So that checks out. So this one says that the mean value theorem and Rolle's theorem apply. Right? Because we have the condition of continuity and differentiability that establishes that the mean value theorem would apply. But then we also have Rolle's theorem applying because of this second condition. Right? So then, if so, apply the appropriate theorem. Well, and I'll take that as a typo. It really should be theorems because it could be more than one, as it is in this case. Right? So we have kind of got a double layer here. Right? So we'll apply the mean value theorem first. Right? For the mean value theorem, I need 2 pieces of information. I need f prime of c, f prime of some value c. But in order to figure that out, I need f of c. I'm sorry, f of x, which we know is x to the 4th minus 8x. And then from there, I need f prime of x, which is 4x cubed minus 8. So f prime of c needs to be equal to f of b minus f of a over b minus a. All right, so there has to be some value c on this closed interval from a to b for which the instantaneous rate is equal to the average rate. Right, so f prime of c would be exactly what I have here in my f prime of x, just replacing every or any x with a c. So for c cubed minus 8. And then for the other part, I'm evaluating the original function. So f of b minus f of a. So the b value is 2. The a value is 0. And we already used that to figure out what f of b minus f of b is and what f of a is, and therefore what f of b minus f of a would be. So it's going to be 0 minus 0 over 2 minus 0, which is going to give us a result of 0. Now, fortunately, we kind of get a 2-for-1 here, in the sense that Rolle's theorem tells us that if we take our derivative and set it equal to 0, we're going to get a meaningful value. Essentially, that's the basis of it. Right? What it's really telling us is that if the y values are the same at the endpoints, then there has to be a relative extremum along the way. That was that wire demonstration I gave last time. Right? So we're going to get both answers with this calculation, which is really nice. So I'm going to add 8 to both sides. I'm going to get 4c cubed is equal to 8, which if I divide both sides by 4, gets me c cubed is equal to 2. So it looks like c is going to be equal to the cube root of 2. Right? And that's fine. I mean, it's going to be some weird decimal answer, but that's perfectly okay. And we could sort of at least attempt to verify that by putting my original function in, f of x equal to x to the 4th minus 8x, right, over the interval of 0 to 2. So squiggly bracket 0 less than or equal to x less than or equal to 2. So it's only this interval that I care about. And you could see the endpoints have the same y value. At 0, we have a y value of 2. At 2, we have a y value of 2. But then we have a turning point here at 1.26. Now, that's almost certainly not an exact value. So what I would do is I pop in, 2 to the 1/3 power is the same as saying the cube root of 2. So 1.26, like the graph is telling us, is really 1.259921 blah blah blah. All right, so we're better off leaving it as the cube root of 2, but that gives us a good sense of what the answer ought to be. Right? So that's the mean value theorem. Now Rolle's theorem would tell us, I'm going to write Rolle's, would tell us that if we took the derivative, and we did, so we have all the same work here, knowing that the endpoints have the same height, the same y value, there must be a point along this domain where the derivative is equal to 0, right? So that actually jumps us right to this step in the process here. So it's all the same stuff, except we wouldn't have had to do any of this work to come up with that 0. We would have assumed the 0, right, by Rolle's theorem. Right, but we would have come up with the same answer only because the average rate of change happened to be equal to 0 over that closed interval. Won't always be the case, as we saw last time, but when it is, it's nice. Now, so that's it for number 5. Number 6, anytime you're dealing with a trig function that doesn't involve exclusively sines and cosines, you want to be careful. And being careful usually means looking out for asymptotes. Right? So if I pop in my original function here, just have a quick look. And that's assuming you're not familiar enough with the tangent ratio in order to know where it's discontinuous and where it's continuous. But let's just kind of play it by the book here. Cosine of x plus tangent of x. Now, there's many instances in which it's not continuous. It's just a question of whether or not one of those instances occurs over this domain, right? Which is over the interval of 0 to pi, right? So looking at this graph, we can see that it's discontinuous. We have a discontinuity at x equals pi over 2. Right? Now, you might look at it and say, well, where are you getting that x equals pi over 2? Well, I'll explain a little bit more about how you can tell from the function in a second. But here's the beginning of the interval at 0. Here's the end of the interval at pi. It looks like the break is about halfway between the beginning and the end. Right? So if you're eyeballing it and you had to take a guess, assuming that it's going to be some nice value, that's probably what you're going to guess. I mean, most people aren't going to be like, well, I think the break is somewhere at 1.5 even, because that's not a nice number. It's not a nice radian measure for a unit circle, right? But let's say we don't recognize that. We could go back to our original function. F of x is equal to cosine of x plus sine x over cosine of x. All right, tangent is sine over cosine. All right, so I would set my denominator equal to 0 to find any discontinuities. All right, so it's undefined when cosine of x is equal to 0 in the unit circle. In the 0 to 2 pi domain, that occurs at pi over 2 and 3 pi over 2. But in this case, because we're only restricted, or we are restricted to 0 to pi, that would happen when x is equal to pi over 2. So that would be the location of a discontinuity, which happens to be on that given interval, right? If there's a break on the interval, if it's not continuous and differentiable throughout the given domain, then neither mean value nor Rolle's theorem would apply, MVT, nor Rolle's theorem apply. All right. Now, if it were continuous, if this was a continuous function over that interval, we would have to check for differentiability just to make sure it didn't come to a point in any capacity. But if a function's discontinuous, then at that location, it would not be differentiable either. Right? So that saves us some time and energy. You don't really have any work to do. Right? But if you could recognize it on site, that makes a big difference. Right. So then we get to the L'Hopital's problems. Right. Some of them I said you should be able to handle based on what we covered last class, and some of them I said it would be unlikely based on the material that I covered. But if you did a little research, you'd probably figure it out. Okay. So when you're applying L'Hopital, we're checking for an indeterminate form. The way we check for that is first by substituting in the limiting constant. In this case, 0. E to the 0 minus 1 times 0 over 0. There's a whole lot of work to say 0 over 0, but we do it anyway. 1 minus 1 over 0 is equal to 0 over 0. That's indeterminate. Which means L'Hopital's rule applies. All right, so if it takes any of the forms in the chart on the previous page, then it would be a L'Hopital's apply situation. So 0 to the 0, 0 divided by 0, any one of these possibilities. So So I'm going to take the derivative of the top and then separately the derivative of the bottom and then reapply the limit, right? But before I even do that, it just kind of makes sense to just do a quick distributive property here. E to the x minus 1, for quality minus, plus x over x. All right, so now we'll take the derivative of the top, derivative of the bottom. Derivative of e to the x is e to the x. Derivative of 0 goes to 1. I'm sorry, goes to 1. Geez, goes to 0. Derivative of x goes to 1. And then on the bottom, the derivative of that x would become a 1. So we're differentiating each part of the fraction and then reapplying the limit. Right? So you see I'm using kind of a more shorthand approach. You know, in the previous problems, I showed you how I was, differentiating the top, differentiating the bottom in separate steps. Kind of an extra step that's not really necessary. You can just sort of do it as opposed to stating that you're going to do it. But at least for this one time, I'll throw in that step. You're saying the derivative with respect to x of e to the x minus 1 plus x over the derivative with respect to x of just x. And then applying that limit again. All right, so that's where this next step, this stuff here came from. All right. Showing that one last step, and then I'm going to retire. All right, but when you apply the limit, we get e to the 0th plus 1 over 1. So 1 plus 1 is 2 over 1 is 2. And so that would be my limit. Now, most, if not all of these problems, you should be able to get a result graphically. It's just a question of can you get the analytic result to match, right? So I can pop this in as y equals or f of x equals, we'll just do y equals this time. E to the x power minus for n 1 minus x over x. You get a nice looking graph here. As x approaches 0 from the left and from the right, like at 0, it's undefined, but from the left, it appears to be approaching 2. From the right, it appears to be decreasing towards 2. So, and graphically, it looks like it's going right through the number 2, right? It's just there is no point there, but there doesn't have to be a point there when you're talking about a limit. It's just what you're aiming for, right? So this seems to check out, so we're in pretty good shape, right? So for the next one, we're looking at when you plug in an infinity, we're going to get infinity squared, which is not an e. That's an e. E to the 5 times infinity. Either way, you're getting some form of infinity on top and some form of infinity on the bottom. Right? That's another indeterminate form. So L'Hopital's rule applies. All right. It's another, at minimum, it's another entry in the table on the previous page, but theoretically, it's the idea that we're looking at 2 different types of infinities. We don't know what they're necessarily going to divide to. All right. So I'm going to apply L'Hopital's rule again, derivative of the top, derivative of the bottom. So 2x up top. Then e to the 5x times 5, which I'm going to write as 5e to the 5x, and then reapply my limit. All right. Now, at first glance, it doesn't seem like it really accomplished much because when I apply my limiting value here, I get 2 times infinity. over 5 times e to the 5 times infinity, which is just another form of infinity over infinity. So that's telling me to apply L'Hopital's rule again. The hope being that if I carry out L'Hopital's rule another iteration, then it'll lead me to something. You know, it'll lead me to something tangible. The derivative of the top, derivative of the bottom. So on top, 2x goes to 2. On the bottom, 5e to the 5x. Derivative of e to the 5x is e to the 5x times 5. So we're going to get 25e to the 5x. Right. So looking at this one, I mean, we could go to the graph just to get a sense of what's going on here, but it looks like we have a constant up top and something infinite on the bottom, which is generally a good thing because that means we're going to lock onto some kind of result. It's just a question of what that result is going to be. But again, there's no reason why you can't look at the graph and say, all right, let me get a sense of what's happening here. This one looks like there's, as you go out to infinity along the x-axis, it looks like you have something that has a horizontal asymptote, if not is exactly on the x-axis, but I'm highly suspicious of that, especially when you're dealing with an exponential function. So you could just kind of zoom in and see that when you zoom in a lot, there is still a little bit of deviation between the function and the x-axis, but this does appear to be asymptotic. So if I had to take a guess just based off the graph, I would think that the limit is going to 0. All right. So that seems to be what's playing out here, because if I plug in infinity for x, I'm going to get a constant 2 over 25e to the 5 times infinity. So 2 over infinity, that's not one of our indeterminate forms. That's something we can determine the value of. Right? Because if we take a constant and divide it by a number that's ever increasing, now we're never going to get to infinity, but we're going to approach the value or the result of this ratio as we get closer and closer to infinity, and that value would be 0. All right. The next couple of problems are a little on the dicier side. I actually want to get rid of this star here. I'm debating whether to come back to those after we do number 6. Yeah, it really doesn't matter. Let me just do them in order. So number 3, we have x times the sine of 1 over x. Now, if I pop in an infinity here, I get something kind of weird going on, and that weirdness happens with the sine of 1 over x. Because if I put an infinity in for x, it seems to give me something that would be undefined. You know, because 1 over the infinity part of it doesn't seem to kind of play out the way we would want it to, you know, in terms of being indeterminate. So we look at our table and we see, you know, like it doesn't quite match up with anything, at least at first glance. But there's sort of a nifty trick that can be applied here, right? So, and I'll show you real quick. So the limit as x approaches infinity, this x can be thought of as an x over 1, right? And that x over 1 it's being multiplied by the sine of 1 over x. But if we took the sine of 1 over x and divided it by 1 over x, by keep change flip, we would have gotten this expression, right? So it's kind of weird that we're sort of going out of our way to make this look like it's indeterminate. the reality is it is indeterminate. It's just not in a form that makes it obvious, right? So it's kind of a nifty trick in the sense that, you know, you look at it and say, oh, I don't know that I would have ever thought to do that, but now you will, right? So just divide by the reciprocal of the thing that's being multiplied. And that's only because what happened here is the result, you know, just kind of thinking backwards. You're probably in the past given this expression and told to simplify it. And when you did so, you did a little keep change flip and you came up with this expression. What I'm asking you to do here is undo that. Because when I plug in for x, I get the sine of 0, really, 1 over infinity, over 1 over infinity, which is sine of 0 over 0, which is 0 over 0, which is an indeterminate form, and telling us that the L'Hopital's rule applies. It's very strange, but it isn't until you get to that transition where you realize, oh, okay, this is a problem I could use L'Hopital's rule for. Right? At first glance, it didn't seem like it was necessarily the case. Right? So then we want to look at this and say, all right, well, now that we know that we can apply it, well, let's try to apply it. All right. So I'm going to rewrite limit as x approaches infinity of sine of x to the negative first power over x to the negative first power. Then I'm going to take the derivative of each part, applying L'Hopital's rule. All right. And so that's going to give me, well, derivative of sine is cosine. Cosine of the inner function, which is x to the negative first power, times the derivative of that inner function, which would be negative x to the negative second. All right. On the bottom, I'm just going to get a clean negative x to the negative second. Still applying the limit as x approaches infinity. And by the way, just like I was saying before, there's no reason why going into the problem, you can't have a quick look at what the limit is supposed to be and go from there. So you'd have sine, I think it was, let me get the original form, x sine of 1 over x. So just pop that in and have a quick look. And see what's going on as you go out to infinity. It looks like it's got a horizontal asymptote. As I go out to infinity, it looks like it's leveling off at 1. So at least I know what I'm supposed to be aiming for. Here I see I have a common factor that can cancel away now, which is really nice. This could be written as the limit as x approaches infinity of the cosine of just a 1 over x, x to the negative first. So then when I apply my limit now, by replacing the x with an infinity, I get cosine of 1 over infinity, which is the same as cosine of 0, which is a 1. So you get your answer, and at least, you know, based off the graph, you go into it knowing, right, if I get a 1, I know I did it right. You know, that's the idea. Let me just shrink this down a little bit. So the next one, limit as x approaches infinity of the natural log of x cubed over the just an x. I'm just going to shrink it a little bit more. All right, so when I pop in an infinity, I'm looking at ln of infinity cubed over infinity. The natural log function, and I'm just going back to that real quick. The simple natural log function. It looks like the kind of function that levels off, but it doesn't. It increases forever, just at a very slow rate. So it'll get there. For the y value will get to infinity. It's just going to do it for a monstrously large value of x. All right. So the infinity for x will be much larger than the infinity for y, or at least the pacing of it. Right. But the bottom line is you're going to get something indeterminate, infinity over infinity. So this is an indeterminate form telling us again that L'Hopital's rule applies. So then I would want to take the derivative of the top separately from the bottom and see where that takes me. If you see something like a simple x in the bottom of a fraction, that's pretty nice, because that's usually telling you that you're on the right track with L'Hopital's rule, in the sense that it's going to cancel out in a pretty nice way, usually. But again, nothing wrong with having a quick look at the function and seeing what you're up against. As we go out to infinity, it does seem like it's leveling off to some extent. Maybe to a 1, kind of hard to tell. It went above a 1 and now it seems to be decreasing. And in fact, it could be even that it's going down to 0. Right, but we'll see. Right, so when we take the derivative of the top, it's a chain rule situation. You got to be careful. It's the whole natural log that's being raised to the third power, not the x. So you can't use the power rule for logarithms. I don't know that I fully understand the question. Maybe you could rephrase that one. Right, so, but I'll try to address that in a minute. So in this case, we're going to say 3 times the derivative of the, 3 times ln of x to the second times the derivative of the inner function, derivative of the natural log of x would be 1 over x. Right? And on the bottom, we're looking at just a clean 1. Right? And the hope is that this will be something simpler and easier to work with, but we'll see in a second. Question for you, inverse of the feature. Oh, gotcha. So if you have something, and so in this case, yeah, it was kind of tricky. When you see something along these lines, the first thing you try to do is make the substitution of infinity in for x. And if you do so, with that substitution, we're looking at infinity times the sine of 1 over infinity, which is really just infinity times 0, which you may recognize as an indeterminate form, but then again, you may not, right? So if you don't recognize it as an indeterminate form, then your first move would be to try to create a fraction out of this, right? And since L'Hopital's rule involves us taking the derivative of the numerator and the denominator separately, you have to have a numerator and denominator to work with. So the only real candidate, I mean, aside from making the sine into a cosecant and putting it in the denominator, which I don't think too many people want to do, the only other candidate for that would be to take that x and make it into the denominator. And the only way to do that would be to keep change flip it so that it went to the bottom of the fraction. Right? That's a good question. Oops, I lost that. So then for number 4, continuing here, we have that 3 natural log squared times 1 over x. You look at it and say, okay, can I now plug in the infinity? Right? So you might want to clean it up a little bit first. If you do so, you get limit as x approaches infinity, 3 paren ln x quantity squared over x. If I plug in infinity, I get 3 ln infinity squared over infinity. It's like, okay, our situation is not improved. You know, it's like we're not quite there, but it actually has improved. It's not improving at a rate that we're thrilled with, right? But if we carry on, we'll see. The fact that we're looking at something that is still indeterminate means that we can go another level of L'Hopital's rule and see what happens, right? So the limit as x approaches infinity, derivative of the top would be 6 natural log of x to the first times 1 over x over 1. Now, if I clean that up, I'll be looking at limit as x approaches infinity of 6 ln x over x. So I was able to reduce my powers by differentiating. Right? So the situation is improving, it just doesn't seem like it is. Right? But if I apply my limit again, I have 6 ln infinity over infinity, still an infinity over infinity situation, still indeterminate, still L'Hopital's rule applies. But now when I take the derivative, I'm getting to a point where I can finally get out of this, this logarithmic purgatory, right? So the derivative of 6 times the natural log of x would be 6 times 1 over x, or just 6 over x, over 1, which is the same as 6 over x. When you apply that limit, you get 6 over infinity. Constant over infinity goes to 0. So it took about 4 levels. It was the 4th level of L'Hopital's rule that got us, oh, 3rd level, sorry, that got us there, but we got it. You know, sometimes it's just a question of perseverance. Number 5 is kind of an interesting one. Let me skip that one for a sec. We'll come back to that because number 6 is much easier. Number 5, it involves kind of a new concept. So it's not really new. It's just applying something in a way that you might not have thought was possible. So I don't want to kind of do any mind-blowing sort of stuff and then go back to the mundane afterwards. Right? But if I apply, so going to number 6 and then back to number 5, if I apply the limit, I'm looking at the square root of 4 minus 0 squared minus 2 over 0 is the square root of 4 is 2. Principal square root, 2 minus 2 is 0 over 0. That's indeterminate form. L'Hopital's rule applies. All right. So I'm going to take the derivative of the top and the derivative of the bottom separately. So this numerator can be rewritten. I probably shouldn't steal that space. I'm going to need it for number 5. It could be rewritten as 4 minus x squared to the 1/2 power minus 2. And the denominator could be, rewritten just as x. So rewritten by not rewriting it at all. So I'm going to take the derivative of each of these, the top by applying the chain rule, and on the bottom, it's just simple power rule. So limit as x approaches 0, we're looking at 1/2 4 minus x squared to the negative 1/2 power times the derivative of what's on the inside, which is just a negative 2x. The constant goes away. The bottom is just going to become a 1. Derivative of x with respect to x is equal to 1. We want to simplify just to make it easier on ourselves when we got to go to the next step of applying the limit and seeing what happens. All right, so this is going to be limit as x approaches 0. I got that common 2 that can cancel out. This 2 along with this one. So we're looking at really negative x over the square root of 4 minus x squared. Can't get a decent radical to save my life here. But that seems to be pretty clean in the sense that we're gonna get a meaningful answer. It's just kind of anticlimactic, I guess. So if I plug in a 0, I'm going to get a 0 on the top and something other than 0 on the bottom. In this case, a 2. So it should give me a result of 0. Although I don't really remember that being the answer. We'll see. Pop it right in and take a look. Could be thinking of a different question too. Or I might have screwed something up. We'll see. The moment of truth awaits. As x approaches 0, survey says 0. Yeah, it's undefined at 0, but as we come in from the left, it appears to be approaching that location. From the right, it appears to be approaching that same location, which has a value of 0. Usually when I don't remember an answer being something, I made a mistake somewhere, but this time, shockingly, I didn't. Kind of nice. So number 5 is the big one. It's a good one. Anyway, yeah, like, I mean, I don't know how, it's not too crazy. It's just, it's different. You know, we'll see. So we have x to the 1 over x power. If you apply the limit, you get infinity. That's not an infinity. I just write characters and hope they make sense. I don't know. Infinity to the 1 over infinity. Now, if we go to our chart here, infinity to the 1 over infinity, infinity to the 1 over infinity. I don't see an infinity to the 1 over infinity. Now, 1 over infinity is the same as, generally speaking, 0. Infinity to the 0th power, infinity to the 0th power. Oh, there we are, infinity to the 0th power. So that's part of our list of indeterminate forms. So we know that L'Hopital's rule can apply here. The problem is, this is an expression that doesn't look like anything we've covered before, which is kind of an issue. Although we have all the skills necessary to be able to handle it, just in a slightly different way, right? It's almost a power function. We get a variable base, but we also have a variable exponent, which means that it's almost an exponential function. The problem is it's almost, and almost is not going to help. I mean, it's not good enough. So close is not good enough. Here's what x to the 1 over x looks like as a graph. I'm going to turn off, honestly, I know what this looks like in a TI. I never even bothered looking to see what it would look like on this calculator. But let me get the x-axis out of here for a sec. It doesn't plot any points. Okay. On the TI, it actually plots some points, but that's kind of immaterial. I'll just make a table here. Oh, that's okay. That explains why. I had it zoomed in like crazy, and that's why it wasn't showing up. So to the right of the x-axis, and let me let me just leave it like this for a second. To the right, sorry, the y-axis, it looks all well and good. Everything's fine. All right, it looks like a decent continuous function. But then to the left, all hell breaks loose. And it's hard to see because it depends on the zoom. The calculator doesn't quite pick it up at all times. But if you go to the table, you see that there are some undefined values. But there are some instances where it's not undefined. Like there's a discontinuous point here that's just disconnected from the rest of the graph at -1. Right? But all the values in between, for whatever reason, don't exist. In -2, I have something that doesn't exist. But if I put in, let's say, a -3, I have a point that exists. -4, an undefined point, but -5 is fine. So then you try something like a decimal value, like -0.5, gives you a value. So you get some points that'll show up on the graph, but for whatever reason, they're not showing up as part of the function, right? And that's because you have a smattering of discontinuous points to the left of the y-axis, all having to do with the nature of the function. But to the right, it's all smooth and continuous and everything's great, right? So somehow that manifests itself into the limit. Now, fortunately, we're looking at something as x approaches infinity, so I'm not overly concerned with what's happening over on the left-hand side, but that will factor in to the nature of the computation. So looking at the limit as x approaches infinity, we can say that this is going to be equal to some value, and we can call it whatever we want. It's starting to glitch on me now, which is aggravating. But let's say we're going to call it L for limit. All right. And this is one of the few times we're going to do this because it hasn't been necessary in other instances. The result of a limit is some value, which is a y value along a graph. But we, in the very early goings of limits, we defined it as some value L for limit. Right? So that's fine. But what I'm going to say here is, why not, since we know that we can use a logarithm, specifically a natural logarithm, to release a variable exponent from being a variable from being an exponent, why not take the natural log of both sides of this equation? Right? So I manufactured an equation out of this by first calling the limit equal to something, saying it's equal to some value L. Now by taking the natural log of both sides, I'm redefining things. I'm saying that the natural log of L is equal to ln of the limit, right? But something that's very often forgotten is that if you find the function of a limit, that's going to be the same as the limit of the function, right? So this natural log, it's complicated as a natural log or as simple as something like a square root, that transcends the limit. That's one of the reasons why they're considered transcendental functions. You can work within or out of the limit just by applying the limit after the fact. The limit as x approaches infinity, instead of saying natural log of that limit, I could say the limit of the natural log of x to the 1 over x. These two expressions mean the same thing. It goes way back to the very beginnings of limits where it never really came up, but it was actually kind of important. If you were to find something like, let's say, for example, the limit as x approached 3 of the square root, let me say x squared. I could write that as the limit as x approaches 3 of x, and then later on square the result. These mean the same thing, right? So that's kind of like the, I'll say the shorthand justification for why this works, or at least the lazy man's justification for why this works. It's not a full-blown proof, but it's an example, right? And so I could do the same thing with a trig function. I could do the same thing with a radical. I can apply the function itself after the fact, right? So that's what's happening here. I'm just choosing to apply the limit, the natural log earlier on, because what that's going to allow me to do is take this exponent and hop it over to log. And then we would say the natural log of L is equal to the limit as x approaches infinity of 1 over x times the natural log of x. Now we've already done something very similar to that. That came up over here. So we know that that's a L'Hopital situation, all right? So on the right-hand side, I could apply my limit here and say that this is equal to 1 over infinity times infinity, which is infinity over infinity, which tells me that L'Hopital's rule still applies. Like a little check-in saying that I'm on the right track, because it still applies. So we're doing something right here. So I can now take the derivative of the top and the derivative of the bottom separately, right? But before I do that, I'm going to rewrite it so that there is a top and a bottom. So the derivative of the top would become a 1 over x. The derivative of the bottom would become a 1. So this boils down to the limit as x approaches infinity of just a 1 over x. I'll bring this back in a minute once I have a little bit more room. All right, which would result, bearing in mind that the left-hand side is still the natural log of L, this is going to result in, when I apply my limit, 1 over infinity, which would be 0, which in turn tells me that ln of L is equal to 0. So then I would just have to think about, all right, under what circumstances would L exist such that the natural log of that value would be equal to 0? And that would just require me to convert back into exponential form. So there's one little bit of a transition left over. ln of L is really the same as the log base e of L. If I convert into exponential form, it would be e to the 0th is equal to L, which gives us a result of 1. So my limit is going to be equal to 1, which is what this graph was trending towards if you scrolled from left to right. Let me just bring it back a little bit. But if you follow that graph, it does appear to be decreasing towards something. That something being a 1. All right, so that's probably the juiciest problem related to L'Hopital's rule that you'll ever see, at least in two-dimensional calculus. Right? But it's all kind of based off of that that idea that you can apply functions to limits in any order before or after you apply the limits. That's something that doesn't come up very often, and when it does, it's like critical to being able to solve a problem. Critical being the word of the day. Critical. So at long last, we can move on to some topics in integration. We're going to start off with something called rectangular approximation. We're not going to do a whole heck of a lot with it tonight, but I do want to get you started with it. All right. And so you have the whole unit 3. You have sigma notation, and my screen is freezing up. Oh, actually, we're not. It just occurred to me. Maybe we don't have to do this rectangular approximation because I'd rather. Well, we'll see. It's just a quick review of sigma notation first, and then we'll see where we're at time-wise. All right. So sigma notation, that capital funky E, is the Greek letter well, for S supposedly, for sum, right? But it's sigma, it's a capital sigma, right? So if you need to find a sum of a certain number of values, you would probably use that form of notation, and it's built into Desmos. It's also built into the TI calculators, right? It's just a matter of finding it. Right? But if you go into miscellaneous, you go to functions, and then go into miscellaneous, you see that it gives you that sigma notation. Right? The A sub I represents the term of the sum, right? And the I is known as the index of summation, and N is it's the nth term. Right. So if we're talking about a finite series here, then we're talking about how many terms. So this is the nth term. Right. And this is the term of the sequence. So when they say find this, it's really not so much about your ability to come up with an answer, because I can, assuming it'll let me, I could pop in an I, 6, I could put in a 1 here, and then I could put in an I here, and it'll give me an answer. It's really more about understanding the expansions, right? So what this is telling me to do is start off with I equals 1 and increase by consecutive values until you reach 6, right? And that's because I've zoomed out on me big time. So we have the I equals 1. That's why we start at the 1. And then our max value is 6. That's why we stop there, right? And we have an expression. So in this case, it's saying start by replacing the I with a 1, then replace by the next consecutive value, which would be a 2, the next consecutive value 3, then 4, then 5, then 6. That summation symbol is telling you to add them all up. All right. So the act of adding it up is not really why we're here. And you can add it up. you'll see as we go forward, it's more of a algebraic process that we're looking for, right? So for the next one, it's saying start with 0. I'm really just going to do a copy paste job here. Start with 0 and increase until you reach a value of 5. Again, by substituting in for I. We're trying to get my color coding going on here. So I'd replace the I with a 0, so 0 plus 1, an I with a 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1. Get those results and add them all up. And that's what this expansion is telling you. But then you start to realize that in some cases, you could have two different looking summations that give the same result. Because once you simplify this a little bit, you realize you're just adding the numbers 1, 2, 3, 4, 5, and 6 again. But maybe you don't recognize that and you pop it all in. And start with I equals 0, going up to 5 instead of going up to from 1 to 6. You see we get the same result, right? And what we're ending up with here is a bit of a transformation, right? These are both linear arguments, whatever's contained within or terms of the sequence. They're both in linear form. And so if we have a translation of one unit, then we can make an adjustment to the bounds of summation to account for that, right? So there, if you start off with an I value, an index value of 0, and you have an expression, you can modify that expression so that you could have an index value of 1, right? But there's an art to that, and we'll learn about that as we go. And there's some basic summation formulas that I can tell you right now, they're not going to have much meaning for us until we dive into some Riemann sums, which I'll explain to you as we go forward. But these are getting at little shortcut rules for anything that follow particular forms in terms of what you could see as the term of the sequence. So like some constant value, C is a constant here. If I is raised to the first power versus second power versus third power. And I'll explain to you why these rules work the way they do as we go forward. But for now, I'm just going to get into this concept of area of a plane region, upper and lower sums. And we're just going to do one example. This whole process here is for you. So I'm going to actually walk you through the process on the next page. But this is kind of like your capsule summary or recap of what we're about to do. All right. So I think it's better taught through examples because it doesn't always really play out when I go through the general procedure or general theory first and then try to explain it in practice. It's usually better the other way around. Right. So in example 1, it says find the upper and lower sums for the region bounded by the graph of f of x equals x squared in the x-axis between x equals 0 and x equals 2 for n equals 4, right? So, and sketch a graph. Well, okay, there's a typo for somebody. I edited this by including the graphs, and I forgot to get the part out where it says sketch a graph. So that's a freebie. But anyway, that n value represents the number of subintervals over the domain, the given domain. Number of subintervals over the given domain. So what we have here is a graph y equals x squared, or f of x equals x squared. That's what each of these curves represent, right? This curve here is f of x is equal to x squared, if only. So f of x is equal to x squared. And so what happened was this graph was made over the interval of 0 to 2, as they said here, x value of 0, x value of 2. That n value is telling us how many times to divide that interval. That interval is divided into quarters. Right? So you split it down the middle, that gives you 2 subintervals, right? From 0 to 1, from 1 to 2. If you split it again, that gives you another set of subintervals. All right. What delta x represents is the width of each subinterval. All right. So if the restricted domain is 2 units long, and we get that by taking the 2 and subtracting from it the 0, because the starting point doesn't necessarily have to be 0. All right. But if we get the difference between the 2 endpoints and then divide it by the number of subintervals, we would get the width of each subinterval, which would be 1/2. All right. And so that makes sense based off what we came up with here. We took that interval of 0 to 2 and chopped it in half again. Each one of these intervals is 1/2 a unit wide. Right? And the same would hold true for the other triangle, geez, the other diagram, but we'll get to that in a second. All right. So what happens is when we're coming up with what we call rectangular approximates, what we're trying to do is approximate the area contained underneath a curve over a particular interval. And if we're using rectangles, there's a couple of ways we could do it. One way would be to work from left to right along that graph, meaning we start at the leftmost part of the graph. And let me get rid of some of this fluff first for a second here. Let's pull that out for a second. We could start at the beginning of whatever interval that we want. And every 1/2 unit, we could plot a point on the curve. And that point could be the upper left-hand point on a rectangle that could be used to approximate the area below the curve. All right. So this rectangle would have 0 height. This one would have, well, whatever that y value is in terms of the units of height. Same deal here. And same deal here. But what we're going to end up with is what's known as an underestimate, right? Because I can fit these rectangles into the curve only so well because I have this constraint when they say 4 subintervals where n is equal to 4, saying the number of rectangles is equal to 4, it's only going to give me so much of an approximation because I'm not going to be able to fill in all this space, right? So that's going to be a pretty sizable underestimate of the overall area, but it's something, right? The other alternative, or the alternative, would be to start on the right-hand side, plot a point, and then half a unit later, plot another point, and half a unit later, plot another point, then half a unit later, plot another point, and then create rectangles out of those. That's really no better because that's going to give me an overestimate of the overall area. Right? It's going to give me too much. Right? But these are really, I mean, there's a third way we could do it, but these are really the the most meaningful ways to come up with an approximation of the area while having at least one point on the curve itself. Right? And that's the whole idea. We want to be able to have a point that's on the curve. And the only way to do that, if it's going to be the top part of the bar, you know, thinking of it as if it were like a bar graph or a histogram. The only way to do that would be to have the left corner be on the curve or the right corner be on the curve. If you got to choose between the two, it's like, well, I don't know which one to go with, so maybe I'll just do both. And in doing so, I'm going to get not enough area here. I'm going to get too much area here, but at least I'll know that my true area is going to be somewhere in between whatever answer I get for this versus whatever answer I get for that. So let's see what I can do here. Really don't need this curve anymore. Bring this back. So what I essentially want to do is figure out the area of each one of these rectangles and then add them all up. So every one of these rectangles, I got this one here. This one's easy enough. That area is going to be equal to 0. This one is going to be something more than 0, and so on. But what I want to be able to do is come up with a generalized approach for this, right? So the values on the x-axis used to find rectangular areas, right? So that's kind of a weird thing, a weird way of representing it. But what I mean by that is the values on the x-axis that correspond with a point on the graph, right? So for that first diagram, that would be 0, 1/2, 1, and 3/2. All right. And we'll carry through the process for the left diagram first and then move on to the right diagram. But really, I mean, I tried to think of a way to try to sort of step by step us through this process. But really, it's just going to boil down to find the width and the height for each one of these rectangles and multiply, right? Base times height, right? So when I say plug each into f of x, f of x is equal to x squared. I'll just make a note of that here. I would get 0, 1/4, 1, and 9/4. What that's telling me is that my coordinate here is 0, 0, 1/2, 1/4, 1, 1, 3/2, 9/4. So when I say plug each x into f of x, I'm just coming up with the y values corresponding with the given x values. All right, so each one of these are the y values. You know, sometimes making a step-by-step process makes the concept, you know, overly complicated. And I feel like, you know, I've never really come up with a nice, concise, easy way of doing this. But it really just comes down to that idea where, I mean, I want to find 2 dimensions to multiply. I would need a base, which I already have, because the base in each case is 1/2. The heights are unknown. I need this height, this height, this height, and this height. And they're all associated with whatever y is at each one of those corresponding values of x. So when I say multiply the values above by delta x, I'm saying when my delta x is 1/2, I'm taking each one of these values and multiplying it by 1/2. I'm going to get 0, 1/8, 1/2, and 9/8. And then I would just add all those up. Right, so just number crunching, 1/8 plus 9/8, for example, is 10/8, which is the same as 5/4. This is the same as saying, let's say 8/4, right? So 13/4, I think. But I'm going to play it safe, I guess. 1/8 plus 1/2. Oh, 7/4. You see, okay, I'm glad I played it safe. So 7/4. All right. So that would be my underestimate. I just came up with an area that I know is going to be less than what the true area is. So whatever the area is bounded between y equals x squared and the x-axis over the interval of 0 to 2 can be no less than 7/4. Now I want to see what it could be no more than. All right. So if I want to come up with dimensions or meaningful dimensions for this scenario, I need each one of these points. I need coordinates for each one of these points. All right. So the relevant x values, it still spans from 0 to 2. Yeah, I got a 0 here. I know I got the 1 in the middle. I got a 2 over here. 3/2. We know that this one is a 1/2. Right. So I need the 2. I need the 3/2. I need the 1 and I need the 1/2. But that 0 doesn't really factor into the computation. Right? Because that's not part of it. Doesn't give me the height of the rectangle. So I would start my computations with x values starting at 1/2, 1, then 3/2, and then 2. At 1/2, I know I have a 1/4. Just plugging it into f of x is equal to x squared. At 1, we know it's 1. It's the same graph, so if 1 gave us 1 before, it'll give us 1 again. 3/2 gives us 9/4. And 2 gives us a 4. Multiply each one of those values by delta x. So the delta x value is still 1/2. The interval is still spaced at 1/2 unit. So 1/8, 1/2, 9/8, and 2. So then I would just add these up. And fortunately, it looks like the computation here is very similar to the previous one. All I got to do is just add another 2 on at the end. And I get 15/4. So on the low end, I'm looking at an area that could be no less than 7/4. On the high end, no greater than 15/4. So from 1.75 to 3.75, somewhere in that neighborhood is where the area bounded under the curve is going to be. Right? It's a process, but this process is going to kind of guide us towards developing what's known as a Riemann sum. And that Riemann sum is going to bring us to what's known as a definite integral. Right? So we don't want to gloss over this process. It's an obscure, it's kind of a weird process, especially when I say, like values on the x-axis used to find rectangular areas, and I call it capital M sub I, but we never refer to M sub I in this whole process. That's kind of building us towards something. I'm calling it M sub I now, and not referring to it as that, but later on we will, and it'll have more meaning. Right? So the next example, which we're not going to do now, but I'm just going to I'll put a star on it so you can have a look at it. But I will also point out there's another typo there. Sketched graph shouldn't be there. But you can see it's the same general structure, except now I have a number of subintervals being n equals 8. So it's really the same process, except now we're going to have 8 rectangles. Now you could probably guess that the accuracy of our rectangular approximation is going to be a little bit better. It's still not going to capture the true area, but it's going to be a little bit better, with the idea being that if we can squeeze in more and more rectangles over that interval, then it'll become more meaningful in terms of an approximation for that bounded region, right? But I also put the wise ass comment at the bottom, who wants to do this for n equals 16, 32, and 256? You know, like the idea of having to do 256 distinct computations doesn't sound overly appealing, right? So with that in mind, there's got to be a shortcut. And that's where we get to, you can see here, we start to generalize it for a general value of n. So that's what we'll be working towards next time we meet. And you can see here, there's that mentioning of the summation. So it's not all for nothing. It's just a little tedious in the beginning, but you start to see why it's why everything is the way it is as we go. All right. Function of approaching. Yeah, exactly. Exactly. So the fact that it's going to be decreasing in terms of rectangles would have us approaching the true area under the curve. And that's actually going to get us to this concept of a definite integral, which leads us to anti-differentiation. So a lot of stuff, a lot of good stuff coming. All right. So with that in mind, I will stop the recording